Hi, I'm Dr. Incognito. In this video, I'm going to introduce limits. So first, a little bit of notation. This is the way limits are denoted. That says the limit as x approaches c of f of x. So we have a function here, f of x, and we're letting the input x vary, and in particular we're letting it approach the value c. So c will be a given number like 2 or 5, or even in some circumstances it could be infinity or negative infinity. So x is approaching some value, and we are interested in the behavior of f of x. So we want to know the limit. What is f of x approaching as x approaches c? And so the first simple question is, well, why not just plug in c? So if you want to know, for example, the limit as x approaches 0 of the sine of x, what's happening to the sine of x as x is closer and closer to 0? Well, why not just say sine of 0? And the sine of 0 is 0. Well, that's absolutely correct, actually. There's nothing wrong with that. You can sometimes just plug in the value that the variable is approaching, just plug it into the function and get an answer. But the reason that limits are important is that there are many times, many situations where you can't just plug that number in to the function. As a simple example, let's say we're doing practically the same thing. Let x approach 0, and instead of just sine x, do sine of x divided by x. So now for this function, 0 is not in the domain. If you were to let x equal 0, you would have a division by 0 here. So 0 is not in the domain of the function. The sine of 0 divided by 0 is not a number. So plugging in x equals 0 won't work. Even simpler, suppose we have the limit as x approaches 0 of 1 over x. Remove that sine function from the situation. This is another situation where the function is not defined at x equals 0. So we can't simply plug 0 in and get an answer. As x approaches 0, what about the sine of 1 over x? Mixing the two. So this situation here, again, x is not allowed to be 0 because we would get the sine of an undefined quantity. So plugging in x equals 0 doesn't work in any of these examples. And x times the sine of 1 over x. There's another interesting one. Plugging in here is controversial, because if you plug in x equals 0, you get a 0 there, and 0 times anything is supposed to be 0. But this sine of 1 over x, when you plug in 0, it's not a number. So when we say 0 times anything, we really mean 0 times a number is 0. And this one, when x is 0, it is not a number. So here are 4 examples where plugging in x equals 0 doesn't work. And in all 4 of these cases, very different things happen. So when we look at the limit as x approaches 0 of f of x in these 4 situations, the behavior is very different. The function behaves differently as x approaches 0 in all 4 of these cases. The simplest looking one is actually the first one. of this function, y equals sine of x divided by x, if we draw a graph of that function, this is the height 1, I'll put an open circle there. The curve looks like that. I put an open circle here because the point 0, 1 is not on the graph. F of 0, this is f of x. F of 0 is undefined. 0 is not in the domain of the function. But the behavior of the function is sort of nice. It's well controlled near 0. So when I look at the limit as x approaches 0 of sine x over x, what that's asking me to do is, in this graph, look at the y coordinates as x, if x is near 0. So if you take an x that's near 0, then the corresponding y coordinate should be near 1. If x is close to 0, then this dot on the curve will be near that open circle. And the height of that open circle is 1, and so the height of that dot is about 1. And as you move the x closer to 0, this dot will get closer to that open circle. We're not actually allowed to let x equal 0, because that we have a problem there, as we discussed. So the limit is necessary in this situation in order to discuss the behavior of the curve at 0. As x approaches 0, this limit, from looking at that graph, is 1. Let's look at the next one. F of x equals 1 over x. The graph of that is a hyperbola. Looks like this. So you can see that the behavior for x near 0 in this example of 1 over x is very different from the behavior for x near 0 in the example of sine of x divided by x. So here, if we want the limit as x approaches 0 of 1 over x, the question is, what is the y coordinate of this graph? What is it approximately equal to if x is very small? So if x is very small, then 1 over x is going to be very big. It's going to be very big. If x is something like 1 over 100, 0.01, then y, which is the reciprocal, is going to be 100, which is pretty high up on the graph here. And so we might be tempted to say, well, let's analyze a little bit further. As x moves closer to 0, then x is shrinking, its reciprocal is growing. So if I make x 1 over 1,000,000, then y is going to be 1,000,000. So as x gets closer to 0, y seems to be growing. And it will grow without bound. And so we are tempted to say maybe use the infinity symbol here. And that's not technically correct because of a small detail. When we're examining this limit as x approaches 0, in the examples in my discussion so far, I've considered x to be positive by default. But that's not necessarily the case. X could be near 0, but it could be negative. In this case, when x gets closer to 0, like negative, if x is negative 1 over 100, then the y coordinate is negative 100. So instead of a large positive number like 100, you get a large negative number like negative 100. And so looking at it from this perspective, as x goes to 0 through the negative values, it looks like the curve is, instead of going up and up and up, without bound. It's going down and down and down without bound. So maybe it's tempting to say the answer here is minus infinity. One person might look at it from this side and say, oh, it looks like minus infinity. Another person here, plus infinity. Who's right? Well, neither really. Both, but neither. And we have a notation to help distinguish these two situations. We could say the limit as x approaches 0 from the right of 1 over x is plus infinity. So we add this little notation here, this superscript plus sign, to insist that x be on the right side of 0. So that means that we're looking at the first situation here. X is on the right side of 0. And in that case, the argument gave us plus infinity. And for the other side, the limit as x approaches 0 from the left of 1 over x is negative infinity. So the left-hand limit is negative infinity. The right-hand limit is plus infinity. And these are very different answers. So if someone says, what is the limit as x approaches 0 of 1 over x, you would have to say, well, technically this limit does not exist because it depends on the direction. If you say x is approaching 0, there are two possible directions of approach, from the left and from the right. So this one is called a two-sided limit. And when the different sides have answers that don't agree, then the best we could do is say that the two-sided limit does not exist. And we can then further describe the situation by discussing the one-sided limits. So the two-sided limit doesn't exist, but the right-hand limit is plus infinity, and the left-hand limit is minus infinity. Okay, so far we've looked at two examples investigating the sine of x over x, which had a nice normal-looking curve here, except it had a hole in it, and then 1 over x, which has a vertical asymptote at x equals 0. And it has these infinite answers in the limit. So very different behaviors. Sine x over x, the limit was 1. Here, you get infinity. The common thing in both situations is that you can't simply plug 0 in. Plugging 0 in doesn't get you anywhere in either case. The next one is also interesting, the limit as x approaches 0 of the sine of 1 over x. The sine of 1 over x. So the graph of this function is a little bit unusual. The sine curve, as we all know, oscillates, and the sine of 1 over x is going to oscillate between minus 1 and 1, and as x gets near 0, it oscillates infinitely frequently. It's capped there at 1 and down there at minus 1, and it oscillates, and as you get closer, as the x gets closer to 0, it oscillates more rapidly. And the same thing happens on the other side. It oscillates between minus 1 and 1, and as you get closer to 0, it oscillates more and more rapidly. And in this situation, the limit as x approaches 0, even just from one side of the sine of 1 over x, just from the right side, this does not exist because the curve is oscillating wildly between minus 1 and 1. It's not approaching a fixed value like this one did. It approached 1. So this limit does not exist due to oscillation. And the same thing for the limit as x goes to 0 from the left. The same thing happens on both sides. You have this, it'll oscillate with greater and greater frequency as x approaches 0, and it oscillates between minus 1 and 1, so it doesn't settle down to a particular value. So 3 examples where you can't plug in 0 and you get something very different in each case. So hopefully this is getting the point across that limits are meaningful for analyzing curves, for analyzing functions and their graphs. The last one was the limit as x approaches 0 of x times the sine of 1 over x. So we just drew the graph of the sine of 1 over x. How does multiplying by x affect it? Well, if we draw the line here, y equals x, and we draw the line here, y equals negative x, then the sine, x times the sine of 1 over x is going to oscillate like this one, but it's going to go between these 2 lines, because this is going to affect the amplitude. So it's going to look maybe something like this. And then as we get x near 0, we'll get this, this wild oscillation. But what's happening is that while the curve is oscillating wildly, it's also being damped by the x. So the amplitude is diminishing. And it looks the same on the other side. It oscillates between the 2 lines, and then it starts to oscillate very, very rapidly near 0. And in this case, though, because of the damping effect of the x, we can see that the limit as x approaches 0, on either side, we will get 0. So here is an introduction to limits, trying to show that when you're calculating a limit, sometimes you can just plug the number right into the function, but those situations are not very interesting when you're analyzing limits. And so most of the problems that you deal with, you won't be able to do that, like these 4 examples. They require some other type of study in order to determine the limit. Simply plugging in the number is not going to get the job done. So in this case, I've drawn graphs of the functions to help us to figure out these limits. And as you can see in all 4 examples, we were doing a limit as x approached 0 of a function where plugging in 0 was not allowed, and we got very different answers in all 4 cases. So you never really know what to expect. When you can't plug a number into a function, there's lots of possibilities for the behavior of the function near that point. Okay, thank you for watching.